This one's going to be about infinite limits and limits to infinity. So limits that are infinite and the limit as x heads towards infinity. Most of this we've kind of touched on already, so this should be pretty easy. In our first lesson on understanding limits, you were confronted with these two situations. Here we're going to begin to compare and contrast the behavior as functions as they approach infinity, as well as functions that tend towards infinity in certain circumstances. So here we go. We're going to use the graphs of f and g shown below to compare and contrast behaviors involving infinity, and then we're going to write our discovery and our definition. We're just going to talk about them. We're not going to write them. Okay, so I have my function. It's already been graphed for me. They've already found the hole. They've already got the asymptotes. Like, they've done all the grunt work for me. I just need to answer these four limits. So as I approach 4 from the left, I am headed towards positive infinity. As I approach 4 from the right, I'm headed to negative infinity. As I approach, oh, that's of G. Okay, there's G. So we need to go down here and look at G. As I approach 1 from the left, negative infinity. As I approach 1 from the right, positive infinity. So your discovery is, when you head towards an asymptote, you're going to be headed towards infinity or negative infinity. Don't need to write that down. Y'all know that. Okay, so those were limits that are infinite. The answer is some sort of infinity. So these are infinite limits, limits that are headed towards infinity, and I want to know what the function is approaching. Okay, so we're going to go back up and look at f, and we're going to head towards negative infinity first. So as x heads towards negative infinity, my graph, my y value of my graph, is headed towards that asymptote at a -2. As f of x heads towards positive infinity, my graph, the y values are headed towards the asymptote at -2. Okay, now let's look at g of x. As I approach negative infinity, this graph is approaching the asymptote, but the asymptote is not constant. It's linear with a slope. So my y values, as x heads to negative infinity, my y values are headed to negative infinity. And as x heads to positive infinity, this function is going to be headed up towards positive infinity. So again, these are x values, these are y values. All right. In pre-cal, you learned some basic truths about rational functions. When a factor canceled from the denominator, a whole happens. When a factor would not cancel from the denominator, an asymptote occurs. Use the previous equations to find the one-sided limits analytically. So these are the functions from the front side, but they're asking us to find these limits analytically, so no graph. Okay, so I already know what all the answers are. It's on the front of this paper, but I need to find it analytically. Okay, first, if you're tootling along and you hit a limit like this, the first thing you're going to do is plug a 4 in, because you have no inkling that it's going to give you an indeterminate form. To save us time, I'm going to tell you that it's going to give you 0 over 0. So the first thing I'm going to do is have really good notation and keep my limit. I'm going to factor it. So let's see. Factoring the top is multi-stepped. I'm going to take a -2 out, but I'm going to do it up here because I don't want to have to write the limit over and over and over again. So now I have -2, 3 and 2, on a +1, +3, -2. And the bottom is just a trinomial, 4 and 2, minus, minus. I now see that the x minus 2's cancel. All right, now where am I headed? I'm headed to a 4. Because that one didn't cancel, I now know that that's an asymptote, not a whole. So I know that my answer to this limit is either going to be infinity or negative infinity. It's not going to be a place. Now, if I took this limit and headed towards 2, it would be a whole, and I would just plug 2 in and get the y value of the whole. Okay, but this is an asymptote. So what I need to do is I need to head towards 4 from the left. So I'm going to go with a 3.9. So I'm going to do -2. 3.9 plus 3 is 6.9. And 3.9 minus 4 is a -0.1. The top is going to be big. It's going to be bigger than 12, negative, but bigger than 12. And the bottom one is a -0.1. Again, remember, we already know that we're headed to either positive infinity or negative infinity. I know that a negative over a negative is a positive. So I know this limit is a positive infinity. Knowing whether it's a whole or an asymptote tells you how to approach the limit. The whole is a place, plug and chug. An asymptote is more theoretical. Think about which side you are approaching from. Pick a number that's on that side of the number, plug it in, and make your decision for infinity or negative infinity. Okay? B, same thing, but I'm headed to 4 from the right. So all of this stays. This and all of this. Okay? But I need to do the limit as x approaches 4 from the right of the 2 and the x plus 3. Okay, the part that's left after you take the whole out. Now I want to fly in towards 4 from the right. So I'm going to plug in a 4.1. And again, I know I'm either going to infinity or negative infinity. So if I plug in a 4.1, 4.1 plus 3 is 7.1. 4.1 minus 4, positive 0.1. That's a positive 14.2. The point is they're both positive. The top is really big, the bottom is really little. That means I'm headed to infinity, positive infinity. Now, let me back up for 1 second. The top is really big and the bottom is really little. And that's why this ratio, when I divide 14 by a tenth, you're saying how many tenths are in 14? Well, it's a bunch. It's a whole bunch. And as this gets smaller and smaller and smaller, as this gets closer and closer and closer to 4, then you're going to be dividing by a smaller number, which is going to make the overall answer get bigger and bigger and bigger. So that's the infinity part. It's positive because both of these values are positive. All right, C. Different function. So again, we're going to plug 1 in and we're going to get 0 over 0. So now I'm going to do the limit as x approaches 1 from the left. Again, good limit notation. Hey, the top doesn't factor. I wonder if you get 0 over 0. Let's try it. I'm just going to plug in a 1. Because, no. Hold on, I'm thinking. This doesn't factor, but this can't be a 1, and nothing's going to cancel, so that has to be an asymptote. So there's a vertical asymptote at 1. It can't be a whole because the top doesn't factor and cancel with it. Therefore, it's an asymptote. So I'm either headed to infinity or negative infinity. I'm headed to 1 from the left, so I'm going to plug in a 0.9. So 0.9 squared, 2 times 0.9, 2 times 0.9 minus 1. This is going to give me something positive, and this is negative, so that's going to give me something negative. Therefore, I know I'm headed towards negative infinity. All right. Okay, make sure you understand how I knew it was an asymptote. I can't just plug in a 1. It would make the bottom 0. The top does not factor, therefore nothing's going to cancel, so I know it's not a whole. So I know there has to be an asymptote at 1, so I'm either going to head towards positive infinity or negative infinity. Okay, same thing on D, same function. I know I have an asymptote at 1, so my answer will be one of those two. I'm headed to 1 from the right, so let me plug in a 1.1. And this is going to give me a positive number on the top, and this one's bigger, so it's a positive on the bottom, so I know it's going to be a positive infinity. Again, I knew it was going to be positive infinity or negative infinity. I'm getting a positive over a positive, so I know it's positive infinity. Let's skip that, and okay, so we'll write this out. I mean, it's kind of Captain Obvious, but here we go. A limit definition or justification of a vertical asymptote. So the way that you know that you're going to have a vertical asymptote is your limit is going to head to infinity or negative infinity. So let's write that out. The limit, so if the limit of x as x approaches c from the right or the left, one of the two, not overall, because most asymptotes don't head to the same place on either side, of f of x is either positive infinity or negative infinity. So if that's true, then x equals c, that's just the vertical line at c, is a vert asymptote. And that should make sense. Okay, removable. Use the function below to find any vertical asymptotes that exist. Justify your answer using limits. Okay, so they've just given me a function. Now I'm supposed to find any vertical asymptotes that exist, but the kicker is I'm supposed to justify my answer using limits. I can't just factor, cancel, and what doesn't cancel state it's a vertical asymptote. I have to show how a limit shows you it's a vertical asymptote. Okay, so let's do the pre-cal part first. Okay, all pre-cal. So I know there's a vertical asymptote at 2. So I have to use a limit to justify that, to define that vertical asymptote. So I have to approach that 2 from the right and from the left. I'm just going to write h of x instead of rewriting that whole function. Okay, so I'm going to use what's left after we take the whole out. And 2 from the right, I'm going to plug in a 2.1. So 2 times 2.1, oh, yeah, minus 1 over 2.1 minus 2. So 4.2 minus 1 would be a 3.2, and 2.1 minus 2 would be a 0.1, and I know that that is headed towards positive infinity. 2 from the left, so I'm going to take a 1.9. So 2 times 1.9 minus 1 over 1.9 minus 2. The top is still positive. The bottom, however, is now negative. So I know he's negative infinity. Okay, so since the limits are headed to infinity on either side, and guys, they don't have to be opposite infinities. Like, it can still both be positive infinity. It still would make an asymptote. So don't think that one has to be positive, one has to be negative. So because the limits from the right and the left both equal infinity or negative infinity, therefore, vert as at x equals 2. Okay. Now we're going to explore limits at infinity, so as x heads to infinity. In order to differentiate between the two conditions, recall lessons from pre-cal relating to analyzing the end behavior of functions. In the exercise below, use this prior knowledge to find each limit of infinity, or at infinity. All right, so we're digging back in the pre-cal archives, and we talked about to the right and to the left, what it would do. And y'all would say it rises, it falls. Now you got to think about what that's based on. Okay, that was based on if the leading coefficient is positive, then it rises to the right. If the leading coefficient is negative, then it falls to the right. If the power, the highest power, so the degree, if the degree, there's an R in there somewhere, if the degree is even, then the right equals the left behavior. If the degree is odd, then the right does not equal the left behavior. That means it does the opposite to the left, because we're going to be headed to positive infinity and negative infinity. Okay, now, guys, all I need is the leading coefficient and the degree. So when I look at this, you need to think about lobstering that out. But you don't need to lobster the whole thing. You just need to go, you need to know the first guy. And he would be a positive 1 x to the 4th. So his leading coefficient is 1. I'm headed to positive infinity, which is to the right. So I'm right here. And since that leading coefficient is positive, I know that I rise to the right. Therefore, I know I'm headed to positive infinity. What this says is this graph heads off into the sunset. It's going to be headed upwards. And think about this. If this is a degree 4, isn't that a W? And doesn't he head to infinity to the right and to positive infinity to the left? And the reason that he heads to infinity to the left is because his degree is even and the left does what the right does. Okay? So for B, we're switching it up. I'm now an odd function, which you know is cubic. Think about that. I'm headed to negative infinity. Well, guys, just based on knowing what that graph is, you know that as you head towards negative infinity, that sucker's headed south to negative infinity. All right, so here's how all this stuff comes into play. Leading coefficient's positive, so I know I rise to the right. Degree is odd, so I know I do the opposite to the left. And that's how I know when x is head towards negative infinity, my y is also headed towards negative infinity. All right. C. Now, C and D are both rational functions. So I need you to think horizontal asymptotes. Not vertical asymptotes. Verticals are the easy ones. That's the denominator should equal to 0. Horizontal asymptotes have to do with the degree of the top and the bottom. If the bottom is bigger, then it's not x. It's y equals 0. If the top is bigger, then there are none. Ooh, that does not say none. None. If the bottom equals the top, then it's y equals a over b, where a and b are the leading coefficients of the top and the bottom. Now, the reason we need to think about horizontal asymptotes is because if you think about, let's say I've got a horizontal asymptote here. This guy, let's say he does this. Oh, okay. As you head towards positive infinity, he's headed towards that horizontal asymptote. As you head towards negative infinity, he's headed to that horizontal asymptote. It's like a magnet. The headed towards infinity or headed towards negative infinity for the y's happens at vertical asymptotes. Okay. So if I'm looking at this guy, his powers are the same. So I know he has a horizontal asymptote at y equals 3. Please don't just write 3. So then I know that as x heads towards positive infinity, this guy's headed towards that horizontal asymptote. So that limit is 3. All right, this one, the bottom degree is bigger. So I know that he has a horizontal asymptote at y equals 0. I'm headed towards negative infinity, so I'm headed out this way. I know that this graph is going to be drawn to that asymptote in the long run, so I know that that limit equals 0. There are only 4 possible outcomes when you explore behavior to the extreme right or left. The curve can increase without bound. So as x heads toward infinity, that one's headed towards infinity. As x heads towards negative infinity, this one's headed towards negative infinity. The curve can become asymptotic to the x-axis. That just means you have a horizontal asymptote at 0. So as x heads toward infinity or to negative infinity, that graph is going to be drawn to 0. The curve can be asymptotic to a specific y value. See, in my mind, C and D are the same thing. They're just pointing out C as being 0 as like this special case. But this is also a horizontal asymptote. So as you ride off into both sunsets, you're headed towards that asymptote, which is a 3. All right, calculus knowledge for asymptotes. Revisiting the rules for finding potential horizontal asymptotes for rational functions from pre-cal, you can use the idea of a limit and calculus to see why those rules hold true. If the degree of the numerator is less than the degree of the denominator, in other words, the bottom is heavy, then the limit is 0. So we're going to write that with a limit. So the limit of the function as it heads off into the sunset towards positive infinity or negative infinity, then the y values are going to be drawn to 0. That's saying you have a horizontal asymptote at y equals 0. This is what you said in pre-cal. This is what they're saying in calculus. If the degree of the numerator equals the degree of the denominator, then the limit is the ratio of the coefficients of the highest degree. So the limit as we ride off into the sunset, either one, of f of x is the coefficient of the top over the coefficient of the bottom. In other words, horizontal asymptote, y equals a over b. If the degree of the numerator is greater than the degree of the denominator, it's top heavy, then the limit does not exist. Technically, they're saying the limit does not exist, but it's headed towards infinity or negative infinity. So I'm going to say the limit does exist because it's headed towards infinity. They're saying infinity is not an exact place. Either way, you're saying that there are none horizontal asymptotes, so there's nothing to pull the graph towards something. So as it rides off into the sunset, it's headed to positive infinity or positive infinity and negative infinity as it heads towards positive infinity and negative infinity. So if you don't have a horizontal asymptote, then that graph is gonna head up or head south. Otherwise, it's going to be drawn towards that asymptote. All right, connecting multiple representations of limits. Example 6, divide every term in the rational expression by the highest power of that x that appears in the denominator. Then apply properties of limits to evaluate each piece to find the limit at infinity end behavior. Yeah, so that's just big fancy stuff for let's apply everything you just learned. Okay, I want you to ignore the graphs. Just look at that function. You're headed towards infinity. Does he have a horizontal asymptote? Because every time your function, if it's a rational function, is headed towards infinity, I want you to think horizontal asymptote. So every time you have a rational function and the limit is headed towards infinity or negative infinity, I want you to think horizontal asymptote. Powers are the same, so it would be y equals a over b, which would be a 2. So his limit's a 2. Now let's come over here to the graph. As x heads to infinity, graph is attracted to the 2. Okay, b, bottom heavy. Should be 0. Yep. As x heads to positive infinity, graph is headed towards 0 because the bottom degree is bigger. Okay, this one, the top degree is bigger. You should have pre-cal flashbacks of when I would say if the top degree is bigger by 1, you had to go find a horizontal asymptote, a slant asymptote. And if you have a slant asymptote, that sucker is still going to head towards infinity or negative infinity. Now, we are headed, so no horizontal asymptote. We are headed to positive infinity. So think about plugging, pretend you don't have a graph. Think about plugging positive infinity into all those x's. The top is going to be infinity squared minus 4 times infinity minus 3, and the bottom is going to be infinity minus 2. So they are both going to be infinite. But think about who's going to get infinite faster. And it's the top because he's squared. Infinity squared. This does nothing. This is little. So this is headed towards positive infinity. As x approaches positive infinity, this graph is going to keep getting, and this is going to keep going forever, and this guy's going to get closer and closer and closer, and he is headed towards infinity. Slowly, but he is headed towards infinity. Okay, so this wasn't awful. It was just tying in the rules that you already knew for horizontal asymptotes to limits as you head towards infinity. So I hope it was a good review of horizontal asymptotes. And the bigger picture is when you look at a limit, remember, use all the stuff that you know. Use your tool belt. Like when you look at C, you don't have to do this. You don't have to plug in. How do you plug in infinity? Well, you got to remember, as you head towards infinity, you need to think about those 3 horizontal asymptote rules.